Hello. Today's topic is about the force of interest. And there are two sections about this concept. For this particular section, we're talking about the situation when the force of interest is constant, which is equivalent to saying that the interest rate, the nominal rate, was compounded continuously. So let's start with the case when the rate is compounded m times a year. Okay, so we have this A1, which is the amount function. Uh, it's accumulation function. So accumulation function, well, if you invest $1, that's amount function. Accumulating function at 1 year. And that equals 1 plus I. Okay, assuming I is the effective annual rate. And that equals 1 plus, this is the effective rate per time period, and then 1 plus that number raised to power by m. So we have this relation. Now, if we take the limit when m goes to infinity, so when m is getting bigger, then you compound it more and more times a year. Say you have a monthly, you have a daily, you have a hourly, maybe secondly, and so forth. So m gets very much bigger and bigger and bigger. So we take a limit and then it becomes compounding continuously. We're gonna use a limit, a very famous limit in calculus, which is something like 1 plus 1 over m to the m, where m goes to infinity. That is e. Okay, e is a number like pi. So we're going to use this formula to work on the limit of this thing, and the limit is 1 plus I, okay? So I have the 1 plus I equals the limit of 1 plus this quantity, and when m goes to infinity. And we rewrite 1 plus. So the limit I told you earlier doesn't require m to be integer. When m is a real number, it's fine. So but the key is that you directly take a limit of that. It doesn't give you an e, okay, because you have this term inside, but you don't have this term outside. So we need to come up with exactly the same form, 1 over m. Yeah, let me write somewhere here. So let's do the 1 plus 1 over x to the x when x goes to infinity. That equals e. So if you have 2 here, then uh, you needed to work with x over 2 here, and then you also get e. But if you don't have don't have 2 outside, it will be e squared. The reason is that you can write it something like this, x over 2. So now that's like one reciprocals, right? And you square that. That would be the same as the original term, and you take a limit. And inside now becomes e, so it's e squared. All right, so we're going to use the same argument. Put m here and divide this by the nominal rate and then multiply by the nominal rate. So I'm not changing everything. I'm not changing anything. And then this inside part would be E. Okay. Uh, we do assume, yeah, that's fine. It's just 1 over 1 over x, and this is x here, so it's fine. And that would be E. And we do assume this thing goes to a number, and we're going to call that number delta. So delta is the limit of the nominal rate when m goes to infinity. Okay. All right. So uh, that equals e to the delta. So 1 plus I would equal to e to delta. Delta is called the force of interest. And then I equals e to the delta minus 1. So that's just a simple algebraic manipulation. And delta equals log of 1 plus I. But these formulas are quite important, so you should be getting very familiar with it. And accumulation function A of t equals e to the delta t. Um, and delta is also the limit of both I, the nominal interest rate and the nominal discount rate. You might have heard about, you learned something from, say, high school about uh, a formula which is called like P times E to the RT. If you put them together, it's like PERT. PERT was a brand of shampoo a few years, probably many years ago. But some people use this to try to memorize this formula. In this formula, this R is basically our delta. Okay, so it's our delta. P is the principal, but when we work with accumulation function, P is 1, so we have e to the delta t. Okay, all right, so these formulas, try to uh, try to remember and understand. Let's look at an example. Jack deposits $12,500 in the 4-year certificate of deposit, the CD, at Community Trust Bank. If the annual percentage yield, APY, which is an effective rate, is 4.235%, find the nominal interest rate delta, convertible continuously. Convertible continuously, that's exactly, it's the meaning of this delta, okay, when m goes to infinity. So delta is the limit of the nominal rate when m goes to infinity. So it's 4-year rate, 4-year period. So what is our let's see, deposit so much money. If the annual percentage rate is that, find the nominal interest rate. Oh, okay. So effective rate is this 1 plus 0, I mean 0.04235. That's the effective rate. That equals to 1 plus I, okay? 1 plus I. That equals e to the delta. So delta would be simply log of 1.04235. If you use calculator, you will get this number to be this. For this particular problem, this number is not relevant. Okay. All right. So this note, you can read it, and I think I just said it similar things. Next example, money at Swift National Bank grows at 3.8% compounded continuously. That's our delta force of interest. Rafael Ortiz closed his savings account at Swift exactly 3 years after he opened it. 3 years, 3 years. And he received his balance, which was this amount. This is capital A of T, okay? 3 years, so A of 3, but let's say just A. Mr. Ortiz made a $60,500 deposit exactly 1 year after he opened the account, but he made no other deposits or withdrawals except for an unspecified opening deposit X. Find X and his balance exactly 2 years after he opened the account. For a problem relatively complicated like this one, I would suggest you to draw a timeline. So I'm going to do that. It usually helps me to clarify many, not clarify, to sort of organize the information in a nice way. Okay, we have 3 year. So one, two. Mr. Otis deposit X dollars at the beginning and then $6,500 exactly 1 year after he opened the account. And the final balance is $24812. So we set up an equation. We have X times uh, ERT, right? E to the delta T. So E to the delta 0.038 T is 3 years. So this is the accumulated value of X at time 3. But then you need to work with the deposit, which is 66,500 in the end of the first year. When the interest, when the force of interest compound, it is constant. You don't need to worry about don't need to worry where you start, where you end. You only need to consider the times elapsed. It's like how many years starting from how many years passed from deposit to the end of the time that you are calculating the amount to at. Okay, so 6,500 times e to the delta t. It has 2 years. That should be equal to 24812. Okay. So you calculate it. I think it should be fine. X is what? Let's try to show you the value. Okay. Okay, that is this number. X is number. All right, maybe I should put the formula here. You have X times e to the 0.038 times 3 plus 6,500 times e to the 0.038 times 2 equals this number. And solve for X, which is this number. Now we're looking for the amount, the balance exactly 2 years after he opened the account, which is at this time. You could use a forward way, but I think the backward way is probably better. The forward way would be X times e to the 0.038 times 2 plus 6,500 times e to the 0.038. Okay, that is this amount, this amount. But you can also do the backward way using this amount. So you discount back, okay? So forward is e to the delta t, and backward would be e to the negative delta t. So that's the discount factor. So you have a 24812 equals uh, which I don't know, but I don't need to set up an equation. I just do this discount times e to the negative 0.038. They should be the same. Okay, these should be the same. Okay. So the previous section is the case when the force of interest is constant, which is not the normal case, which is a compounding interest scheme. But now let's look at the general theory. We have a accumulation function at, which may not be an exponential function like what we did earlier. We have earlier like 1 plus I to the n or e to the delta t, something like that. We're going to define the force of interest to be the derivative of log of accumulation function or the derivative divided by the derivative of the accumulation function divided by accumulation function. Okay. The force of interest tells us how well an investment is doing near a particular point in time. So it's continuous, so it's an instantaneous rate. Uh, the force of interest is higher than you accumulating more interest around the time. Uh, and if it's smaller, then it's weaker. Okay. All right. This is kind of a definition, so you need to know very well. Okay, let's work on a few examples. This one is our amount function, and then we're looking for the uh, we're looking for time actually. Delta t is 0.5. So to find delta t, I think use log function is pretty easy. We actually don't need to work with the principal. We only need to work with the amount function. Sorry, the accumulation function, which is this. So you take a log of that. So delta t equals the derivative of a log function of a of t, and so log of 1 plus t over 4 to the third, and then I take the derivative. So that equals 3 times log of 1 plus t over 4, and then take a derivative. 3 obviously is a constant. And the log function, log x, the derivative is 1 over x. So you have 1 over 1 plus t over 4. And here's t. But then you need to use the chain rule, the derivative of the inside, which is 1 over 4. That is our delta t. So sort of simplify it. You have a 4 plus t on the bottom, and that should be equal to 0.5. And we're looking for t, and you solve for t equals 2. Okay, that's the answer. All right. The next one, we're looking for delta t for simple interest r. Remember, for simple interest r, the accumulation function is 1 plus rt. It's linear. Okay, it's linear. And I think it's easier to use the a prime t over at instead of taking log. Essentially, they're the same, but it's probably simpler. So delta t equals a prime t divided by a of t. A prime t equals r, the denominator 1 plus r times t. Okay. Now I want you to notice that this delta t is decreasing with respect to t. So when t gets bigger, delta gets smaller. I should put t here. All right. That means the force of interest is smaller in the longer term, and you understand the bank doesn't like that. So normally, a simple interest is only used for a short period of time. The compounding interest scheme is fair because the force of interest is a constant, so it's fair to both borrower and the lender. All right, so let's work with the simple discount. Remember, the simple discount, the accumulation function is not linear, okay? So the discount function is the 1 minus dt. The accumulation function is actually 1 over that. So it's actually not linear. So let's find the log. Yeah, log or yeah, log is probably easier. So find the delta t. So delta t is log of a of t. Then you take the derivative. Log a of t is negative log of 1 minus dt, and they take the derivative. That is negative and 1 over 1 minus dt, and then you multiply by the derivative inside, which is negative d. So you would have d over 1 minus dt, which is here. Okay, so this is the force of interest. It's kind of interesting when t gets bigger, bigger, and bigger, and then it gets small. It gets actually possibly negative. Right. So again, a simple discount, simple interest, they are usually used when t is small. All right, so what is delta t for compounding interest at an effective rate I? We know delta t should be a constant. That's in a previous section. But nevertheless, 1 plus I to the delta t, sorry, it's 1 plus I to the t. That's our uh, accumulation function. And then you find log function. So delta t is log of 1 plus I to the t, then take a derivative. You pull out this t from the exponent, okay, and take the derivative. And it's a linear function actually in terms of t. So the answer is log 1 plus I. So it's a constant. And that's exactly what we denoted it in the previous section. It's delta. And we have e to the delta equals 1 plus I. Delta is log of 1 plus I. I equals e delta, e to the delta minus 1. Okay, all these relation you should be familiar with after some practice. All right, so this problem. We have accumulation function a of t, and we are looking for delta t. Uh, This for this example, obviously log a of t is very useful instead of doing a prime t over a t. That's actually quite complicated because you have a product of three terms and you differentiate them. It's a little bit more complicated. It's unnecessary to do that. So let's do the uh, to do the what the log function, okay? So delta t equals log of a of t, then take the derivative. And then log of the product equals the sum of the logs. So I have t over, well, maybe another step. Okay. So I have a log of 1.05 to the t divided by 2 plus log 1.04 to the t squared over 2 plus log of 1.03 to t to the third over 6. And then you take a derivative with respect to t. And I can simplify further, so t over 2 times log of 1.05 plus t squared over 2 times log of 1.04 plus t to the third over 6 times log of 1.03. And then you differentiate it with respect to t. I would get 1/2 log of 1.05 and then plus uh, that is log, hold on a second, I think I made a mistake somewhere. It should be 3 instead of 2. I said 3, but I still wrote 2, 3. And then I have a 2t over 3 times log 1.04 plus 3 to 6 can cancel out 3. You have a t squared over 2 log 1.03. I think parentheses probably not necessarily. All right, and then you combine them. So that equals log of 1.05 to the half plus log of 1.04 to the 2t over 3 plus log of 1.03 to the t squared over 2, and then put them together. Again, log of the sum of the logs equals log of the products. So that's the answer. Okay. All right. So in the previous slides, we talk about how to get delta t from AT. So you know AT, the cumulative function, you differentiate, you take a log, differentiate, you get delta t. Okay, so how to get AT from delta t? You literally solve the differential equation. Okay, so delta t equals log of A of t, take a derivative. So you integrate it, okay, from 0 to t, and delta need to do r because you sort of need to use t for this upper limit, and equals log of A of t plus some constant. This constant, you can get to the constant to be 0 because you plug in t equaling 0. So the left side will be 0. And use the fact that A of 0 equals 1 because we are working with accumulation function, and it's assumed that you invest $1 to the account. And log of 1 is 0, so C equals 0. So based on that, I'm going to get rid of this C. And then you have A of t equals e to the integral from 0 to t delta r dr. Okay, so we have this equation. So AT is determined based on delta t. Okay, and also obviously delta t is determined based on A of t. So they have a sort of a one-one relation. All right. Let's look at an example. Suppose delta t equals 3 over 1 minus 3t. Find the corresponding accumulation function of t. I would just work it out. There's nothing fancy to think about. So a of t equals e to the integral. Let's do the integral first. 0 to t, delta r, 3 over 1 minus 3r, and then you do dr. This is just a linear log function. Log of 1 minus 3t. Well, actually, we need to do 1 minus 3r, and then from r from 0 to t. Okay, so let's do 1 minus 3r. So first of all, check. Differentiate it, you get 1 minus 3r. Oh, actually, there's a negative sign somewhere. Okay. I normally just write down and check and to correct it. Because log of 1 minus 3r, you differentiate it, and it's pretty easy to see it's 3 over 1 minus 3r with this negative sign. And then you do r from 0 to t, but when r equals 0, you get log 1, which is 0. So I have negative log 1 minus 3t. Okay. So I have a of t equals e to the integral, right? So negative log of 1 minus 3t. Put this negative inside, so you would have e to the log n, and you can cancel out 1 minus 3t to the negative 1. So it's this is the base e, right? Exponential was base e, and log was base e. You composite two functions, they cancel out because they are inverse functions. So it's 1 minus 3t to the negative 1. Okay. All right. I think there's probably another example. A fund accumulates at a simple interest rate of 5%. Simple interest. Another fund accumulates at a compound interest rate 4%. Well, the 5% is bigger than 4%. Okay. Compounded yearly. 4% is compounded yearly. When will the force of interest be the same for two funds? After this point, which fund will have a higher force of interest? We know that the simple interest rate gives you a decreasing force of interest. So at the beginning it's 5%, but then gradually will get to smaller, and at certain point it hits 4%, and then later it will be smaller than 4%. So after this point, which fund will have a higher force of interest? I know that's the second fund. All right, let's try to figure out when they're going to hit. They have the same force of interest. So basically, you set up equation, you find the force of interest for the simple interest scheme, and then the other one, and then you equate them. Remember, for compound interest rate, we have a constant force of interest. So A of t for the simple interest, we have 1 plus RT, okay, 1 plus 0.05 times t. Actually, we did earlier for the force of interest, but we can do it again. Is the A of t differentiated. So delta of t equals A prime t over A of t. So that equals 0.05 over 1 plus 0.05 t. It's here. And the right side is the compound scheme. So we have delta equals log of 1 plus I. Okay. So that equals log of 1.04. And you solve for t. T is that. Okay. Another example. A deposit of $10 is invested at a time 2 years. Using a force of interest of delta t, which is a decreasing function, well, t cannot be too big, cannot be greater than 10 years. So find accumulated value of this payment at the end of 5 years. Uh, we're dominated by this force of interest, delta t, starting from 0. So from year 2 to year 5, the force of interest is determined by delta t. It will be different from the force of interest from 0 to 3 years. Okay, you need to know that because delta t is not a constant, number. Okay, so we sort of need to do some discount using the accumulation function. Okay, that's kind of important. If you like, you can draw a timeline. And you have 0 here, 5, 5. So 1, 2, 3, 4, and 5. So it's 5 here. And you have 2 here. And this is dominated by delta t, okay? So we need to find A of t. A of t equals e to the from 0 to t delta r, so 0 0.0, 0 0.2 minus 0 0.02 r dr. Okay, so that equals e to the 0 0.2 t minus half, 0 0.01 times half r. Antiderivative, okay? Find antiderivative. And when r equals 0, and it's obviously 0, so you just plug in when r equals t. So t squared. Okay, so this is our a of t. Now, uh, this is $10 here. And we're looking for the accumulated value at this point. So what you can do is, I'm gonna move to another place. So you need to discount back using the delta t here, or a t here, okay? And then you need to do this, okay? That's the right way to do. So you do 10 times 1 over a2, and then accumulate to time 5, so we do that. At is here, so you can directly plug in, so 10 times 8, 5, so e to the 0 0.2 times 5 minus 0.01 times 5 squared. And then you divide it by a of 2, which is e to the 0.2 times 2 minus 0.01 times 2 squared. Uh, Certainly you can do that. Or we have this because I'm going to just show you why this is true, okay? You can use this formula. That's no problem. So let's do that. A of t equals e to the integral from 0 to t delta r dr, okay? So a5 over a2, that equals e integral from 0 to 5 delta r dr, and divided by e to the integral from 0 to 2 delta r dr. And then you have exponents, the ratio of the exponents with the same base is the e to, well, I mean, base is e to the difference. So you have 0, integral from 0 to 5 delta r dr minus integral from 0 to 2 delta r dr. And we have the property in Cal 1 that the difference between these two integrals would be just the integral from 2 to 5 delta r dr. We can change r to t, that's no problem, as long as there's no confusion in the formula, because we have sort of t somewhere there, so it's a bit confusing and you need to change t to r. Once that's gone, you can change to t delta r dr, delta t dt, delta s ds. It doesn't really matter at all. Okay, so we have that. All right, let's see, are there any examples left? I'm not, yeah. Inflation, I think, uh, maybe I'll quickly go over this. Example, I guess hold on a second. I need to get back, it's not this one. I'll quickly go over this, meaning, and inflation is the loss of purchasing power per dollar. It's a very common thing in reality. So if PT is the price level at time t, so usually determined by a basket of goods, and then we define inflation rate R. Some people use R for interest rate, but we're going to use this for the inflation rate. R of T1 to T2, so it's a time period, okay? Also, it's time not period, it's a some time period, yeah. That equals the price at T2 minus price at T1 divided by price at T1. And then the inflation adjusted interest rate J is 1 plus I over 1 plus R. So you're gonna sort of treating R as like discount. Uh, it's not the discount rate, okay? It's different from discount rate. It's kind of treating the discount factor, 1 over 1 plus R, okay? And then J would be I minus R. Let's just do the algebra, okay? It's just algebra to get this. And then example, I think once you understand the formula, it's probably it should not be very difficult. So let's look at the example. Now, when $10,000 was invested by Kelly at time zero, the inflation rate is expected to be 3%. She wishes to have 4% growth in buying power. That's the inflation adjusted rate. Okay, that's her expectation. Find the lowest interest rate at which she'd be willing to invest. So I have 1 plus j equals 1 plus I over 1 plus r. And j is what she expected. And I don't know what I is. We need to look for it. And the inflation rate 0.03. So I equals 1 plus 1.04 times 1.03 minus 1. Okay. All right. All right. Um, B, if I equals 8, find the growth of buying power, which is J. So you just use this formula. You're gonna plug 8% for I. So you have 1 plus 0.08 over 1 plus 0.03 minus 1, you would get the J. If I equals 8%, but R equals 3%, 3.5%, find the growth of the buying power. They're pretty similar. So it's 1.08 over 1.035 minus 1. You will get that number. Okay. All right. That's about this section, this section of this chapter. Okay, we finished chapter 1. Uh, that's for today. Bye bye.